any rate, well, we're going to get started. Now, I have a lot of material that I want to go through, so I want to get started on this. And I'm going to talk about climate change, and I've been pretty busy the last 2 weeks kind of preparing for this. I did a lecture on this last year, and I looked at it. It really needed some improvement. So what I've done is I've gone back to a climatology textbook, and kind of what I've done is I've gone over some real basic stuff. I'm going to be talking about this over the next 2 weeks. This week I'm going to be talking about some very basic things about climatology, and it's going to look, I'm going to try to make it as simple as I can. None of us are climatologists, but one of the things that you'll find as economists, we're kind of naturally interested in physics. The models of economics come from physics, so we learn a lot of mathematics, so we get comfortable with all that. And actually, there's a lot of the math here is understandable to economists. The other thing is that this is a very important issue. It's a very, very important issue for economists. So I think it's something that we need to understand at a very good level, enough of the science, so that we have some idea what climate scientists are talking about when they tell us about about their findings. And so that's what I'm going to do today, is talk about some very basic science of the Earth's climate. As I say, this is very basic, but I think it's I've gone over this material carefully, and I think it's a reasonable start. And what I'll do first is I'll show you, this is the land and ocean global temperature anomaly. This is from the National Oceanic Atmospheric Administration of the United States. And this shows the temperature anomaly is you take the average temperature globally, you take an average temperature globally, say in a month, and then you take all of an average over a number of years, and then you compare the difference between the temperature in a certain month with the average temperature over a long period of time, and the difference is called the anomaly. So that's what this is the departure from the average, and the average is based on 1900 to 2000. So from 1900 to 2000, that's 0. The average there in that period is 0. So anything above 0 is above the average over the 1900 to 2000 period. Below 0 is below average, and you can see there's a clear kind of upward. It's a little bit flat, a little bit down, a little bit up, a little bit down, a little bit up, but a general upward trend. And we can see, say, from around 1900, about minus 0.25, that we've had an increase of roughly in 100 plus years, 115 years, an increase of about 1 degree Celsius in average global temperatures. That's the best, I think that's the easiest way to read it. And then we can also observe, an increase in atmospheric carbon dioxide. And this is something I've taken from Antarctic ice core. This is the Law Dome Antarctic ice core. It's quite famous ice core. And what this does is it shows when you drill an ice core, what you're doing is you're capturing, within that are bubbles of air in the ice. So in the ice are bubbles of air that have been there that tell you it's a sample of the air from when the ice was formed, when it was at the surface. So if you're drilling and you go down, and what they've done here is 2,000 years. So going back 2,000 years, and you're taking little samples of of air, and you can measure to see what the content and the amount of carbon dioxide in the air. Carbon dioxide mixes quite well in the atmosphere. So it's what's called a well-mixed greenhouse gas. So if there's any, and also at Antarctica, there are no plants. There's no plants, it's all ice. You're talking about high on the Antarctic plateau. And so you can get a very good measurement of over a long period of time, the amount of carbon dioxide in the atmosphere. So this goes back 2,000 years, but I've taken it from 1775. As we've talked about, 1775 is the approximate time that the Industrial Revolution began. So that's why I've chosen this date, and that's about your 280. This shows that this was the right around the start of the industrial era, 280 parts per million. This is in parts per million. So you take a million parts in the atmosphere, that's 280. So that is 2.028%. It's not a very big number, but that is the amount of carbon dioxide in the atmosphere. We'll see it does have, changes do have an impact. We'll see that changes have an impact. But you can see that here's 1800 about here, and you do start seeing some impact. Even that far back, there was some, in Britain, you were starting to burn coal, or the invention of the steam engine. There was the beginnings of the use of coal to create energy. So you started seeing some upswing, and then we talked about around 1850. Here you get that. Now you're starting to get that to go up. So this is when the real Industrial Revolution begins to kick in right here, and it's going up steady, steady. This is after World War II. Here's World War II. It ends about right there. Now you see it going up. This, I think I've spliced a couple of, I think what I did here was this is right to the point that I used this, and then I used another, source. I'm going to have to check that, but I think that's what I did here. That's why you have that. But this is, now you can see a very steady, and it's increasing rate of carbon dioxide in the atmosphere. From the late 1940s, it was about 300, 310. Now we passed 400, so 400 parts per million. And so the question is, we go back, see that increase in temperature. That's from the 1880s, and you can see there seems to be some relationship between the amount of carbon dioxide in the atmosphere and the Earth's temperature. And so what we're going to do here is talk about how that could impact the temperature. And the important factor there is what is the process, what is the way in which the increase in carbon dioxide in the atmosphere may be impacting the Earth's temperature, and how much that's going to be. And so that's the direction of what we're going to do. But in order to understand that, we have to understand the Earth's climate. And so what I'm going to do, we know that it's largely due to human activity, the increase in atmospheric carbon dioxide. We burn fossil fuels in order to create energy, and we know that the burning of fossil fuels pumps carbon dioxide into the atmosphere, and that's caused that to increase. So we basically know that. So that raises the following questions. If there's a connection between the two, what is the strength of the relationship between the observed increase in carbon dioxide and the observed increase in surface temperatures? Two, if the relationship is strong, then human activity has had a measurable impact on global surface temperatures over the past century. If that's the case, well, human beings have thrived on the Earth during this period, but the global population has dramatically increased. We're living better now than we ever have. So far, it's quite difficult to argue that this caused any major problems. The burning of fossil fuels so far has clearly been an overall positive. But it's reasonable to ask, will that be the case in the future? That's certainly a reasonable question to ask. And if we consider that a relatively small portion, and I think this is a very important point, because it's still a relatively small portion of the human population is fully benefited economically from the Industrial Revolution. We live in a country here that has, the country that I'm from has benefited tremendously. I think Nazir, your country is pretty well off because of its average income is quite high. So I think your country is part of that as well. But still, there's a lot of the world it has not. Now we've seen, for example, this big increase. A lot of that's China. A lot of that is spent in this century. A huge portion of that increase is because of the economic development of China. And yet there are still billions of people. Probably half the world's population is still quite poor. Half the world's population is still relatively poor, and they live in countries that are relatively poor. India, for example, is beginning to develop. Well, then it's very reasonable to expect a dramatic increase in the level of CO2, carbon dioxide, in the atmosphere in the future. So now we need to ask, will such an anticipated increase be a problem? And if so, how big of a problem? So that's the important question. How big of a problem is it going to be? Now, as I say, as economists, we're not climate scientists, but we do have training in mathematics. Our models are basically models from physics. So I think we have a natural interest in things that are physics. I know certainly even though I'm an economist, I'm certainly interested in physical science, and certainly I have enough mathematics that I can at least look at these things and have some understanding of what's going on. So that's what I want to also talk to you about, that's some of the things you want to think about in terms of some of the mathematics that you need to learn, and the things that you can understand by learning that mathematics. But I'm going to attempt to introduce some important concepts to provide you with minimum understanding of the basic science behind climate change. But I do want to emphasize, I'm not claiming to be an expert. I don't claim to be an expert, but one of the things that you'll has anybody studied climate science in any great detail? Basic. Okay, so I'd be interested to see if this is what you've studied. So that'll be, what I'm going to talk about. So yeah, please let me know. I'm interested to know that. So what I'm going to cover the following topics in this lecture. The natural variations in greenhouse gases and the human-induced changes since the beginning of the Industrial Revolution. It's kind of the same thing. That I covered that very quickly. I'm going to spend a lot of time giving an overview of the climate system, including the energy flows, the hydrological cycle, that's the water, so the way that water cycles through the system, and the carbon cycle, the way that carbon cycles through the Earth's physical system. Please note there are a number of other cycles. That nitrous oxide is one, phosphate is another, and there's one other, and I can't think of it right now. But these are what are called biochemical cycles, and all these cycles combine to produce impacts on as these chemicals and the energy and chemicals cycle through the Earth's system. They can produce changes in the climate. And because human beings are causing some changes in that, then the changes that human beings are causing can have an impact on the climate. So we're going to do this overview. As I say, I'm going to be talking about the hydrological cycle and the carbon cycle, but there's a few other cycles I won't be going over. We just don't have any time to talk about that. I'm going to talk about the physics of the greenhouse effect. It's important to understand, have a good feeling for what the greenhouse effect really is. With greenhouse, if you may know, a greenhouse is where you have a building and it's plastic or glass, and plants grow under it, the sun comes through it and holds heat in. So we call the atmosphere's ability to retain heat the greenhouse effect. It's not a very good name. It's not an accurate term, but that's the term we use. But I'm going to talk about the physics of that. I'm going to talk about what's called radiative forcing. So this is what happens basically when we change the gases in the atmosphere. Greenhouse gases in the atmosphere, and specifically carbon dioxide and methane, and that produces what's called a radiative forcing. And what that means is we're putting those gases in the atmosphere, it changes the balance, it retains more energy in the atmosphere, which causes changes. Basically, it's a forcing, it forces changes to the amount of energy to be retained in the atmosphere. So we're going to talk about that. Radiative dampening talks about how the Earth, a new equilibrium is achieved in the process, that when there's a forcing, a change in the composition of the atmosphere, how then that results in a change in the temperature at the Earth's surface. Then we're going to talk about climate feedbacks and climate sensitivity. I don't have this prepared as lecture material. I may introduce this topic today. I'll certainly be talking about these in the next lecture. These are the very important, climate feedbacks and climate sensitivity are the most important aspects of climate science as it relates to the increase in greenhouse gases. And this is something that most people do not understand. And this is one of the most important things that we need to learn here. And all of this topic is so that you can understand that this is the really important thing. Our climate feedbacks, they're feedbacks as a result of changes in the atmosphere. And what is the sensitivity of the climate? What is the sensitivity of the Earth's temperature to a doubling of the amount of carbon dioxide in the atmosphere? That's typically how climate sensitivity is defined. That says if we double the amount or the effective amount of carbon dioxide in the atmosphere from 280, as we see here, there's from the original 280 to 560, what is going to be the impact on the eventual final impact on the temperature at the surface of the Earth, on the average temperature at the surface of the Earth. As I say, we're only going to cover a portion of the basic science. I've used a textbook. This is Global Warming, the Hard Science by L.D. Denny Harvey. It's quite technical. It's quite a technical, full-on climatology textbook. So I've used the first 3 chapters of that to put the lecture together. I want to also point out, I'm not going to talk about aerosols. Aerosols and their effect on the climate, that includes sea salt, dust, soot, and sulfate particles. They're a significant part of the climate system. They probably have more of an effect on cooling. And in fact, the sulfate particles and soot might be getting in the news, because if you're following the news in the Bali, the volcano on Bali that is beginning to, has a little bit of an eruption. I've been to Bali and I've been near that volcano. It's quite that's a big volcano, and it's had caused a lot of, I think about 50 years ago it had a big, the last big major eruption was 50 years ago. if there's a major eruption of a volcano like that, that can actually impact the entire global climate for at least some time. The last major eruption was the Mount Pinatubo and Mount Harvey. There were actually two that were in Chile in 1991, 1992, and those had an impact. Those reduced the global temperature. And I remember that was around the time that I came to this country, and it was excessively cloudy and rainy and a little bit cool here. So I remember my first 2 years here were excessively cloudy. So that is, they're significant, but really talking about it, it just makes things very, way too complicated to talk about in a lecture on the essential features of the climate. So just keep that in mind. The first thing is we're going to talk about natural variations in greenhouse gases. And as I say, we're talking about the greenhouse, the so-called greenhouse effect. And as I mentioned a little bit earlier, the analogy between a greenhouse and the physics of what we call the greenhouse effect is actually quite poor. And you'll see this. You'll understand this by the end of the lecture. The greenhouse effects represents the trapping of solar radiation by the Earth's atmosphere that enables the Earth's temperature to stay within a range reasonable to support life on this planet. The temperature of the Earth's surface is probably about 15 degrees or so Celsius. The average surface temperature would be 0 Celsius without, we wouldn't have but that's the impact that the atmosphere does. Carbon dioxide is the most important greenhouse gas in the atmosphere and whose concentration humans are directly influencing. We'll explain exactly how much that is a little bit later. The average atmospheric concentration is increased from about 280 parts per million at the beginning of the Industrial Revolution to just over 400 parts per million at the present. A little bit, we're going to talk about methane. That's also an important greenhouse gas, not quite as important as carbon dioxide, but it has also increased, and it has had some impact on the amount of observable warming as well. It's very likely. The available evidence suggests that the atmospheric concentration of CO2 has been significantly higher for much of the last 500 million years, and this is quite interesting. It's thought the evidence is that the amount of CO2 in the atmosphere may have ranged between 4 and 16 times the current amount. So for much of the past 500 million years, which is a lot of time, we've actually had a lot higher levels of carbon dioxide. Now we know there have been times in the past where the Earth was much warmer than in present. I think when the dinosaurs were running around, they had a lot more warm weather. We also, Antarctica, for example, was once tropical. Although that also was probably because Antarctica was once located not at the South Pole, but away from the pole at one time. So it was in a different place, but it was once had somewhat of a tropical climate. So we know that there's been a big range. More recently, there's been the significant range there has been significant range observed in the atmosphere's natural level over the past 160,000 years. And it's naturally varied between 180 parts per million and 300 parts per million. So even over the last 160,000 years, what we've seen at the 18th century was relatively a little bit higher than what we've seen. And basically, the Earth has been relatively cool. For much of this period. The Earth has been relatively cool for much of the last 160,000 years. So that's some of the things that people have seen and thinking, well, that may have some significant impact. And I just want to also point out the natural level of methane, CH4, has varied between 0.3 parts per million and 0.7 parts per million. So there are some natural variations. And we'll talk a little bit about that, and you can see why the way the Earth cycles carbon has an impact on, and carbon can take longer to go through that cycle, and so that can have, that can well have an impact on that, on the amount of carbon in the atmosphere. So there are 5 major components of the Earth's climate system. The first is, of course, the atmosphere. Now what's interesting here is you'll see there's the atmosphere, but I've got the Earth, and I've got water, and there's clouds, and then I've got the oceans, but I got the atmosphere, and I've got clouds, and then this is the oceans, and then this is the biosphere. The biosphere are things that grow, the living things on the planet. The most important things are plants. Plants probably have the most important impact. So but again, we're seeing the atmosphere and a little bit of water as well there. So the water and the atmosphere are all pretty closely and closely linked. They are all quite closely linked, as we'll see. Then we have what's called the cryosphere, and that's the ice on the planet. The Earth does have a significant amount of ice. Much of that is in Antarctica and in Greenland. There's also, of course, the polar ice cap at the North Pole. That's a much thinner ice, but there are enormous amounts of ice both at Greenland and in Antarctica. Probably, I think the thickest is about 3.5 kilometers thick of ice. So there's some that's a lot of ice. So that represents, I think about 2% of the total amount of water is in ice, but that can change over time. For example, if the Earth cools a little bit, then the mountains and mountain plateaus can have more snow. We've had periods where there was the ice ages in the northern hemisphere, so there were increases in the amount of ice cover. So this can vary. And finally, in terms of the climate system, this includes what's called the lithosphere. That's the crust and underneath the Earth. And what we'll see is that, especially through the carbon cycle, that carbon is pushed down to the bottom of the oceans, and then through subduction and the movement of the Earth's plates, then carbon is pushed into the lithosphere, and then, as we'll see, and what happens is from the lithosphere, through volcanic activity, carbon dioxide, carbon is recycled back into the Earth's atmosphere. So that's we'll see that's part of how the carbon cycle works. And so that's why the lithosphere, even though it's below the surface, is a part of the Earth's climate system. It's part of how the Earth regulates, how climate is regulated over long periods, and how it affects the composition of the atmosphere. So we need to keep this in mind. But there are 2 areas that are not considered part of the climate system, and those are the sun. And you say, well, that's interesting. Isn't the sun the sun essentially is the source of energy? We wouldn't have it, if we don't have the sun, we have nothing. And that's true, but both the sun and the volcanic system, and that's Mount Krakatoa in Indonesia, that both the volcanoes and the sun are what we call exogenous. They're out to the system. They're outside of the climate system. So those are outside of the climate system. They affect the climate system. They have an impact on the climate system, but they are not affected by the climate system. Volcanoes are still going to erupt no matter what happens to the climate system, and the sun is going to shine no matter what happens to the Earth's climate system. So these are outside of the Earth's climate system. Now, in the case of volcanoes, the volcanoes do pump carbon dioxide. It's part of this carbon cycle and recycling carbon back into the atmosphere, but the volcanoes themselves are not directly a part of the climate system. And of course, the sun is important, and the sun has variations in the amount that it shines, but that variation doesn't appear to have as much of an impact, so that's something we're not going to focus on in this lecture. And most climate scientists don't think that small variations in the amount of solar radiation have a big impact, and I think there's pretty reasonable to understand why. Now we're going to talk about the climate system overview. And the components of the Earth's climate system are linked by flows of energy and matter, and they include solar and infrared radiation, sensible heat, that is heat that can be directly sensed, latent heat, that's heat related to changes in the state of water. You change water from a liquid to a gas, gas to a liquid, liquid to a solid. Either there's energy that's used to cause that to happen, or energy is released. But there's latent energy. There's energy within water, and then the transfer of heat energy between the atmosphere and the ocean. So those are the main components of the Earth's climate system. As I say, they're all linked through energy and matter flows. Then important consideration is solar radiation wavelengths. This is very important because the solar radiates in these these are the most important frequencies of electromagnetic radiation that come to the Earth. And that is ultraviolet radiation, and that's 0.1 to 0.4, that's microns, millionths of a meter. That's the wavelength. That's the wavelength of ultraviolet light. Visible light is 0.4 to 0.7 microns. The near infrared is 0.7 to 4.0. Those are all, that's all radiation that is emitted by the sun and that reaches the Earth. Now, it's also important to remember that when two things, one, that most of the UV radiation that the sun is absorbed in the atmosphere by ozone, that's O3. So ozone, which is up in the stratosphere, absorbs most of the UV radiation that reaches the, so it doesn't reach the Earth's surface, which is good for us. That's certainly good for our form of, the most forms of life on the planet. So visible light and near-infrared radiation reach to the atmosphere and the Earth's surface, where it's either reflected or absorbed. And if it's absorbed, reflected just means it bounces off and goes back into space, and if it does that, it just has the same wavelength and it disappears. It's as if it never happened. It comes in, if it's reflected, it shoots back out into space. It's like it never happened. But if it is absorbed either by the atmosphere, clouds, the atmosphere, or the Earth's surface, then it's re-emitted as longer wave infrared radiation that is, ranges between 4 microns and 50 microns. That's longer wave. That means it has less energy. So if you think about it, think about on a hot day, the sun is beating down on the Earth. That's short wave. Much of that is near infrared. Some of that's visible light, but much of that is also the near infrared. It's absorbed by the Earth, and then it's released as longer wave radiation. So you can't see it. If you could see it, it would be visible light or near infrared. But it's released as longer wave infrared radiation, but you could feel it. You can feel the heat, of course, and that's from the energy that's being released, but it's done through longer wavelengths. And that's very important as well, because the gases in the atmosphere that absorb long wave radiation. They don't absorb short wave radiation for the most part. So that's a very important consideration. Earth energy flow. This is the big picture. The Earth's energy flow consists of the inflow of solar radiation to the atmosphere and the Earth's surface, as I mentioned, either shorter wave visible light or near infrared radiation. So the reflection or absorption of this radiation and the remission of the absorbed shorter wave radiation is long wave infrared radiation by the atmosphere and the Earth's surface. So we can measure we have a measurement of the amount of energy that flows into the atmosphere of this infrared and visible light radiation, and it's measured in what's called watts per square meter. So square meter, the amount of radiation, the average amount during the year over the whole Earth's surface. So this is a big average. There's tremendous variations depending if you're in the tropics or at the poles. Of course, at night that's zero. That's incoming, so it depends on the time of day. All of that, but if you average all of that out per square meter on the Earth's surface, on average, the inflow is 342 watts per meter squared. So that's an important thing. I've seen other, you'll get these figures are somewhere near that, 342, 343. But that's the inflow. Now, since energy is conserved, now what that means is that energy is essentially not destroyed. If it flows in, ultimately it has to flow out. So the energy has to flow out. I've used this dark color, this dark brown to indicate shortwave radiation. And then the dark and then the lighter brown color, this is to signify long wave radiation. It's cooler, it's longer waves, and a mixture of that flows out, but it's the same. The outflow and the inflow are exactly the same. So there's a balance. So there's always a balance. So that's a very important thing to remember, a balance, and it's about 342 watts per meter squared in and outflow. So keep that number in mind, 342, because now we're going to break that up. We're going to break that up and we're going to look at that, and as economists, we can look, we're kind of like accountants. We're used to counting things and categorizing, and so think this is a real basic, some very basic things that all of us as economists can understand. So incoming shortwave radiation, there's four things that can happen. It can be reflected by clouds, aerosols in the atmosphere. Reflected, just comes in, boom, goes back out. It can be reflected by the Earth's surface. It can be absorbed by the atmosphere. And it can be absorbed by the surface. Those are the four things that can happen to incoming radiation. So we'll now look and see, well, what are the things that happen? The total amount of reflected that reflects back into space is estimated, and these are estimations. They're, if you look at different places, you find a little bit different figures. But here, what I showed, the source says it's 107 watts per meter squared. Absorbed is ultimately absorbed is 235 watts. So the incoming solar radiation, 235 watts per meter squared are absorbed, 107 are reflected, so roughly about 30%. So about 30% of the total is reflected back into space. That total, if 30% gets reflected back into space, again, it's like it never happened. It's like it went around. If it came in and said, "I'm going to be reflected, I'll just go around the Earth," it won't have no impact. It's as if it didn't happen. So it just reflects back into space as if nothing happens. So what we're talking about is this amount that's absorbed. Oh, and I also want to point out, here. Let's say this is probably not too far off from the surface of the moon, for example. The surface of the moon is about the same, pretty much the same distance from the sun as the Earth. It's going to have that amount of radiation as well, and it's going to have short and long wave radiation, but there's no atmosphere, so that's going to be the difference. So now let's look at what's reflected. The part that's reflected by clouds, aerosols in the atmosphere, most of the reflection is done in the atmosphere. It's 77 watts. Of the 107, 75% or so is reflected by the clouds in the atmosphere, aerosols in the atmosphere, and 30 watts per meter squared are reflected by the Earth's surface. So that means of most of what reaches the Earth's surface, you'll see that 130 and 168, 80% is absorbed. So if it reaches the Earth's surface, 80% is absorbed, a relatively small amount is reflected. So then absorbed by the atmosphere, 67 watts per meter squared are absorbed by the atmosphere, and 168 watts per meter squared are absorbed by the Earth's surface. You see that? That adds up to 235, and that adds up to the 107. So I've broken out that and that into that. So there's a fair amount that's absorbed in the atmosphere, and also an amount that's absorbed by the Earth's surface. So this is what's going to cause warming. This is what creates our climate. This is what causes our warming. This is what we're interested in, is what gets absorbed. The reflection, it's gone. We really don't care about that. So now, let's see. Did I get that right? Yeah, okay. Now I'm going to look at the outflow accounting. As I mentioned, this is basically, it can be, the visible shortwave can be reflected as visible and shortwave infrared radiation, or it can be emitted as long-wave radiation. I've discussed that. So 107 is reflected, 235 is emitted. This goes, that goes back out. As we said, 167, this is 67, 168. I'm just putting that into a single file to show the 235 watts per meter squared of incoming shortwave solar radiation. Okay, so this is just basically repeating and reorganizing what I did on the previous slide. Now, we're going to now talk about the total inflow accounting. And this is what's very important, and this is where it gets very interesting. We know that there's a total of 235 watts per meter squared of shortwave radiation that's absorbed either by the Earth's atmosphere or it's by its surface. So 235 watts comes in. Whenever the shortwave radiation is absorbed, then it must be emitted, and when it's emitted, is emitted as longer wave radiation in this, of this wavelength. So the atmosphere has some ability to retain this longer wave radiation, and some of it eventually makes its way back to the Earth's surface. So it hits the short wave hits the Earth's surface, it's absorbed, not what's reflected. Reflected is gone, but the one that's absorbed, re-emitted as long wave radiation, is then captured, absorbed in the atmosphere, and then re-emitted back to the surface. And that's kind of the process that's going on, and that's part of what we call the effect of the greenhouse effect. So here's the total amount as we talk. Here's the shortwave radiation absorbed by the Earth's surface. This is what comes to the Earth's surface directly from the sun. Then here's long wave radiation absorbed by the Earth's surface. That doesn't come from the sun. That is radiation that either goes into the atmosphere, is absorbed by the atmosphere, and then re-emitted as long-wave radiation that makes its way to the Earth's surface, or long-wave radiation that has been, short-wave radiation hits the Earth's surface, long-wave radiation that goes back up and then comes back down. So either way, eventually that gets back down to the Earth's surface. And this, here's the interesting point, 235 watts per square meter is absorbed by the atmosphere at the surface. The total amount of radiation, and eventually we don't care what the radiation is. We don't care what it is, it's radiation. So the total amount of both short and long wave radiation that reaches the Earth's surface is 492 watts per meter squared. So that's much higher than the amount that's of shortwave radiation that's absorbed either by the Earth's atmosphere or by its surface. So this is the magnification of the amount of solar radiation, the amount of radiation that reaches the Earth's surface. Now 492, now let's just go back, because the total incoming solar radiation, remember, is 342. That figure 342, but 492. So we have total from the sun is 342, but 492 reaches the Earth's surface. That's what happens. That is so it's an increase in radiation, and that's the effect of the atmosphere. Okay, so it's approximately double that of the shortwave radiation absorbed by the Earth's surface. So that means that the Earth's surface temperature is much greater, is greater than it would be without the presence of the Earth's atmosphere. And it's on average about 15 degrees Celsius warmer. And I think the Earth's average temperature is about 15, so it would be about 0, and everything would be kind of be freezing without the greenhouse, some type of greenhouse effect. Now we're going to look at the total inflow and outflow, because this is now a very subtle and important point about how the atmosphere works and how the greenhouse effect works. And then eventually, when we consider that, we're going to consider the impact that putting greenhouse gases by human activity into the atmosphere has on affecting the Earth's temperature. So 492 watts per meter squared is the total radiation absorbed by the Earth's surface. But the total radiation emitted by the Earth's surface is only 390. So look at this again. So 492 of both short and long wave radiation comes in, 390 is emitted. So there's an excess absorption. There's an excess of about 100 watts per meter squared here. So now there's that excess of energy. But as we said, the total amount of energy that goes out, that leaves the Earth's atmosphere, has to be balanced with the amount of energy that comes in from the sun. So the amount that ultimately goes out has to be the same. The same 342 comes in, 342 goes out. But we have roughly 100 watts per square meter at the Earth's surface of excess. Well, there has to be a balance somewhere, and the balance is in the atmosphere. We showed earlier the total amount of radiation leaving the atmosphere must be the same. So the excess radiation absorbed at the surface is offset by an excess of radiation emitted by the atmosphere. Okay, so the atmosphere absorbs about 67 watts per meter squared of atmosphere area, of surface. You can consider it as surface area. Think of it not as volume, but as surface area. And the total radiation emitted by the atmosphere is 165 watts per meter squared. So this difference is excess radiation on 98. This is just because these figures are approximate, they're not exact, but it's at roughly 100. 100 is of excess absorption at the surface. Excess radiation in the atmosphere is about 100. That's the balance. So that's the balance. The atmosphere radiates more total radiation than it absorbs, and the Earth's surface absorbs more radiation than it emits. But it does have to be in balance. So this is also beginning to tell us the impact of the atmosphere on retaining heat. We're beginning to see how this process works. So I said a total of 492 watts per meter squared reaches the Earth's surface, and since only 390 watts per meter squared are emitted, there's that excess. So what happens to that excess 102 watts per meter squared of energy? Well, this excess energy doesn't just sit on the Earth's surface. It gets transferred into the atmosphere, but it's not done by long-wave radiation. It's done this excess energy is transferred between the surface and the atmosphere, and that energy transfer is what we call weather. That's what weather is this excess transfer of about 100 watts, 102 watts per meter squared that gets transferred to the atmosphere, and it's done in two ways. One is through what's called evapotranspiration, and that's plants. Plants absorb plants into photosynthesis absorb solar radiation, and they absorb solar radiation, and they release so that they absorb water vapor, solar radiation. They absorb radiation, they release radiation, and also the Earth itself is that's transpiration. That's the effect of plants, and then the effect of just water evaporating then water evaporating and transpiration. That pushes 78 watts per meter squared. That's that total that goes into the atmosphere as heat. It goes in as heat, as not as it's in the form of what we call sensible heat. We can feel that heat. It's not radiation. It's in the form of heat. And then the other 24 watts per meter squared are what's called thermal heat, and that's through the air bubbles, pockets of air that transform. Warm air rises, cold air sinks. So warm air at the surface rises. This is what's called thermal heat. And that heat will rise into the atmosphere. And this helps to form clouds. The thermal heat rising into the atmosphere helps to form clouds. The evapotranspiration brings water vapor into the atmosphere. And in fact, this evapotranspiration then creates what's called latent heat. Which is the heat in the atmosphere that then precipitates back to the Earth's surface as rainfall. And so that 78 watts per square meter goes up in the atmosphere and rains back down, and there's a constant overturn of this energy. And in fact, an important point is that the entire amount of water vapor in the atmosphere, all of the water vapor in the atmosphere is completely turns over in only 8 days. Every 8 days, the entire water vapor, the whole water vapor in the atmosphere is replaced. And it's a completely different, it falls down as precipitation, more of it goes, and it's just an 8-day cycle. That's the length of time that the entire atmosphere is the complete overturning of that. So this is a constant process of this that goes up. Now the thing to remember is that it's not even. These things vary. So if they vary and there's energy transfers, that's what I said about the latent heat and release back to the Earth through precipitation, that creates additional energy transfers. Since you have different heating, different amounts of energy going into the atmosphere, and yet the atmosphere is air and it flows, so if you have different intensities of energy, that's warmer or higher density or lower density, those things are going to create differences in pressure and density, and that's going to flow within the system. And so you get horizontal, you get different transfers of heat energy across the planet. And some of these important transfers include horizontal transfers of sensible and latent heat in the atmosphere. A lot of that goes in the tropics, and it can spread towards the poles. Land, cold air from the polar air comes south and north, depending upon which hemisphere you're in. So there's the transfers of cold and heat that take place. That's horizontal in the atmosphere. The atmospheric heat transfers from the tropics in the direction. This can be anywhere on the Earth's surface. That's A. That's anywhere on the Earth's surface. B, we're talking about atmospheric heat transfers from the tropics in the direction of the poles. The tropics are much warmer, and there's going to be a general transfer of heat towards the poles. That heat is distributed in the direction of the poles. Horizontal transfers of sensible heat in the oceans from the tropics in the direction of the poles. And the way that works is that at the poles, especially in the North Pole, because there's more water in the North Pole. At the South Pole is surrounded by land. Cold water sinks. Cold water is heavier. It sinks to the bottom. That flow flows from the poles and down through the bottom of the Earth's oceans all around the world. So when you go down to the bottom of the ocean, even in the tropics, at the bottom of the ocean, it's almost zero. It's like 2 degrees, 0 to 2 degrees at the bottom of the ocean. So that's very cold, and that's come from the poles. So the poles so the water cycles from the poles to the Earth's oceans. There's warm air that goes that's transferred in the direction of the poles from the tropics. There's also very complicated flows of both warm air and water. We don't have time to go into that in this lecture, but just be aware that it's a very complicated circulations. I'm just talking about very brief over. It's very interesting stuff if you're interested in it, but and if you are, I urge you to go further into the topic. I just don't have the time. I don't believe I'll have the time to go into that. I think I'm going to get through this though, I think. Hydrological cycle. This is the most important cycle in the Earth's climate. And it represents the cycling of water between the Earth's ocean and its continental areas. So the amount of water is apparently fixed. I mean, there could be more. You know, probably our water on the Earth comes from comets. There's probably some water that may come in, but pretty much it's the relative net flow, at least in the short term, is zero. So flows within the hydrological system are expressing what are called gigatons. And this 1 gigaton is 1 billion metric tons of water. So 1 billion, there's some cubic mass of, maybe it's cubic kilometer? I think I'd have to figure that out. It's probably a cubic kilometer. Or is it 1,000? Anyway, so we begin with the hydrological flow in the oceans. So in the oceans, these are the volumes, and so you'll want to keep these in mind when we think about that and compare with the carbon cycle in terms of the amount of water vapor. 419,000 gigatons per year annual through the world's oceans evaporate into the air. So over the oceans, that's that lighter blue. The darker blue represents precipitation. 382,000 gigatons per year precipitates in the oceans. So what that means is that 37,000 gigatons per year that goes from the ocean into the atmosphere doesn't fall back down as rain in the ocean. Well, it's got to go somewhere, and that somewhere is to the continents. So there's a net evaporation of 37,000 gigatons per year in the Earth's oceans. So we can look and see, so there's a net evaporation, so it must go from the flow from the atmosphere over the oceans to the atmosphere over the Earth's land area. But it flows in both directions. There's flows in both directions. From the ocean to the land is a flow of 94,000 gigatons per year. So you've got this excess of 37,000, but 94,000 flows from the ocean to the land. 57,000 gigatons flows from the land to the oceans. So there is an exchange, of course. The atmosphere is over both land and ocean, so there's going to be an exchange between those, but the net flow is from the ocean to the land of 37,000 gigatons per year, and that's the balance. The balance there, that's the net flow, 37,000 gigatons per year of water that goes from the oceans to the Earth's continents. And so that is the net flow, that is the flow of water in the hydrological cycle. And so now we'll consider the flow on the Earth's continents. The evapotranspiration, we talked about, that's both evaporation and the transpiration, the breathing of primarily of plants. That releases 69,000 gigatons per year of evaporation and transpiration into the atmosphere. That's a lot smaller number. So you can see the oceans, so that evaporation, 69,000 gigatons per year, and the oceans 382,000. The thing to remember also is that the land area is about 30%, oceans are about 70% of the Earth areas. That has some impact, but still per square meter of surface there's a lot less total evaporation. And there's more precipitation. So there's more precipitation than there's evaporation because the liquid, the water vapor that has come from the ocean. So there's a net flow, and again, 37,000. So there's a net precipitation gain of 37,000 gigatons per year in the Earth's continent. So, and I mentioned this earlier, the entire amount of water in the atmosphere is replaced by evaporation and precipitation every 8 days. So there's a net precipitation gain of 37,000 gigatons per year in the Earth's continental areas. So by definition, the continental areas are above sea level. They better be, or else we're going to be swimming. So, now there's some areas in the interior that may be below sea level. There's a few, very, very few areas in the world, but we're above, on average, we're above sea level, which means that's got to flow. It doesn't stay on the land, it flows. It's higher, it flows to a lower gravity, and the gravity is it flows back to the ocean. So the ocean and the land, obviously, there's the 0 gigaton. I just want to check and make sure this is running. Yes, good. Ocean and land, of course, 0 gigaton per year, else we'd be in big trouble. The land and the ocean, and that's through rivers, primarily through rivers, 37,000 gigatons, also some glacial activity as well, but 37,000 gigatons per year for a net flow of 37,000 gigatons a year from the land back to the ocean. That's the cycle. That's very simply, it's really not that complicated. It's actually quite simple. It's quite simple cycle, and yet very important. It's a very, very important cycle. And in fact, as we will see, water vapor is the most important greenhouse gas. So this is a very important consideration. Water vapor is the central part of our discussion. Even though we're talking about carbon dioxide and other greenhouse gases and the impact of human beings in changing that, this is the most important discussion that we can have, is to talk about the hydrological cycle and the effect of water vapor in the atmosphere. And with that in mind, we'll now turn to the carbon cycle. Carbon cycle is very, now that the carbon cycle regulates 2 important greenhouse gases, carbon dioxide and methane, that's CO2 and CH4. They're both carbon. You can see they both have, that's the C, that's that represents carbon, a carbon atom in each of those molecules. The flow of carbon in the carbon cycle is far more complicated. The Earth, you'll see the Earth's hydrological cycle is quite simple compared to the carbon cycle. And yet the carbon cycle has some very, very important impacts on the Earth's climate. And probably a lot more than we'll see just based on what seems to be fairly small amounts. Fairly small amounts. But at any rate, it's far more complicated because carbon occurs in different chemical forms in different carbon reservoirs. And this is way beyond, the discussion of the different chemical forms is way beyond this class and this lecture. I assure you, it's quite complicated, complex stuff. I don't have much of a chemistry background myself, so I can look at it, okay. I can see what they're talking about, but I'd have to do a lot of studying myself to really understand it. So that's in different chemical forms, very, very complicated. The transfer process between carbon reservoirs is much more complicated than the case with the hydrological cycle. It's much more complicated. So the carbon reservoirs include all of the ones with the atmosphere, the biosphere, the plants, that's primarily plants, the soil, surface ocean, the deep ocean, and the lithosphere. So carbon flows between all of these, these following those elements in the climate system. All of those are part of the carbon cycle. So the atmosphere interacts strongly both with the biosphere, that's living things, and with the soil. And the atmosphere also interacts strongly with the surface ocean. So the surface ocean interacts strongly with the deep ocean, but the deep ocean and the atmosphere are very weak interaction. It's very weak, and it's also weak between the soil and the surface ocean. There's a weak, although it's very crucial interaction between the deep ocean and the lithosphere. And we'll see basically, essentially, there's a net sinking of carbon from the atmosphere through the soil, through the Earth system, the continents, and into the deep ocean, and then into the lithosphere where it's re-emitted by primarily volcanic activity. So that's the kind of big picture of the carbon flow. We'll start with the approximate amount of carbon in each reservoir. These numbers are considered very rough. And that's the thing to remember here. This science it's a young science, and these are figures that are quite very rough figures. 560 gigatons in the atmosphere. Now we noted how in over the oceans there's it's 400,000 gigatons of water vapor that are evaporated annually. There's 560 gigatons of carbon in the atmosphere. It's a lot smaller figure. The biosphere is thought to have 720 gigatons, so it's roughly equal to the atmosphere. The soil is thought to be 1,200 gigatons, about the amount, roughly the amount of the atmosphere and the biosphere. The respiration, photosynthesis draws 120 gigatons of carbon out of the atmosphere. So when plants absorb carbon dioxide, and when plants photosynthesize, the sun, they absorb solar radiation, and through the process of photosynthesis, absorb carbon dioxide out of the atmosphere, and they breathe oxygen. Or they exhale oxygen, and they draw in carbon dioxide. We do the opposite. We draw in oxygen and exhale carbon dioxide. So we do exactly the opposite of what plants do. So that's the photosynthesis, 120 gigatons per year comes from the atmosphere. That's quite a bit. So there's a lot of turnover. So you can see right away through the biosphere and the soil, there's a lot of turnover of carbon in the total amount of carbon in the atmosphere. 60 gigatons is respirated back into the atmosphere from the biosphere. Now the soil, the interesting thing here is the textbook that I looked at doesn't talk about the transfer between the biosphere and the soil, and I don't understand that. It just didn't even mention it. I'm looking and saying, well, there's got to be a transfer here. Where does it? If this is going up, almost 60 gigatons is going up, and it's got to come in somewhere. So presumably, I think what you're doing is you're getting 120, so there's a 60 excess, and that 60 is flowing to soils, but they're not very specific. I suspect that's what that is, because when plants die, then a certain amount of carbon in the plants is absorbed into the soil. That's probably what's going on. So that excess then flows into the soil. So there should be some kind of arrow there. Now you'll notice carbon dioxide, the methane CH4, very small amount that flows, 0.2 gigatons per year. It's not a lot. The methane, methane's very small amounts. It has a lot more of an impact than carbon dioxide per molecule, but there's a lot less of it, and we'll see the total impact of methane is much smaller than carbon dioxide. Roughly, well, this is very, very rough, even though it says 59.3. There's, from the soil, almost 60 gigatons. So it's almost a complete cycle, but not entirely, because some of it flows from the ocean or from the soil. The carbon is removed in the rivers and it flows into the surface ocean. And that's about 0.5 gigatons per year. These are small numbers, but we'll see they kind of add up. They add up, and it does end up pumping carbon into the deep ocean. So that's where we're going with this. But that is basically the interaction in the carbon cycle between the surface biosphere, the soil, and the atmosphere, and then the interaction between the soil, the continents, and the surface ocean. Now, and I haven't. And one thing that I'm not going to talk about here, but there's also some carbon dioxide is removed from the atmosphere chemically through the interaction of the atmosphere with rocks, with what are called silicates. But we're not talking about the silicate cycle, so it's, again, it is part of the discussion, but there's no time to discuss that here, but just keep in mind carbon dioxide is removed from the atmosphere also through the weathering of rocks. It's quite interesting, and that is through silicate rocks that have silicate compounds. That there is a net removal, but again, it's a complex chemical reaction that's beyond, I think, is beyond this discussion. Continue with the carbon cycle. We're now looking at the interaction between the surface ocean and the atmosphere. And there's a, oh, I'm sorry, I've got, that's wrong. Sorry, that should be that way. That's 100, it's 100 up, 100 down, sorry. So that's about a balance of carbon flow. The surface ocean absorbs carbon dioxide, and also there's the release of carbon into the atmosphere by the surface, and it's a rough balance. There's also some flow from river water that flows into the ocean. Some of that goes up into the atmosphere, and some percentage goes down. So that's 1 minus A. That's A is the percentage of the water that flows into the ocean from the continents, and then 1 minus A is the amount that flows into the deep ocean. Sorry, I'll have to fix that. The biosphere is there are plants in the ocean, as you're probably well aware of. Plankton and other there are plants. They photosynthesize. Some of those are not plants, but there are plants. They photosynthesize, and it's actually quite a large amount of respiration, because it withdraws through photosynthesis in the water about 50 gigatons per year, and respiration is about 40, even though it's only about 3 gigatons of carbon within the biosphere, within the living organisms in the ocean. And you'll notice that that is a much smaller figure than in the biosphere, much, much smaller than on land, and yet there's quite a bit of turnover anyway. So there's a lot of photosynthesis going on there. Now we talk about the deep surface ocean, the biosphere. This is where, and again, we don't have time to talk about this, but there's essentially what's called a biological pump, and it overcomes the pressure to push carbon compounds up. It essentially pushes it lower, and it's very roughly thought to be about 10 gigatons per year into the deep ocean. The important point here is look at the amount of carbon in the deep ocean. It's 38,000. There's 560 gigatons in the atmosphere. 560 gigatons in the atmosphere, 38,000 gigatons in the deep ocean. That's a lot. Most of the carbon's in the deep ocean. And the process, this chemical process, means basically that there's a very low concentration of carbon dioxide in the atmosphere. And again, it's too complicated to explain here, but this does cause, this chemical process in the nature of the Earth's oceans causes a very small amount of carbon dioxide to be present in the Earth's atmosphere. It's very different from Mars and Venus, which have very high concentrations of carbon dioxide in their atmosphere. I think Venus is almost like over 90%. It's pretty high. It's actually very high on Mars too, although much thinner atmosphere. Earth, a very, very low amount of carbon dioxide. This B gigatons, there's some amount, it's a guess, 10 gigatons per year. And the B means it's buried. It's buried by subduction, subduction of the Earth's plates. The carbon absorbs into the deep ocean. It falls to the deep ocean through a chemical process called the biological pump. And then the Earth's plate then carries that into the lithosphere, and then it will eventually cycle through volcanic activity back into the atmosphere. It can take, which is can be thousands of years process that we're talking about here. There's the linkages between the biochemical cycles and climate. Now we're going to start talking about feedback, because this is the really important point. A feedback represents a change from the existing state through some variable producing a change in a second variable. There's some change in A, which causes a change in B, and the change in B then causes some change in A. That's what's called a feedback, and this represents the change from the original state of A as a result of the change in B. Positive feedback is when the change that's caused that from A then goes to B, and then the feedback back to A produces the same direction. That's a positive, or the same direction, either positive or negative. That's a positive feedback. When it's the opposite direction, that's called a negative feedback. Some increase to B produces a decrease. A decrease to B produces an increase. Positive feedbacks amplify the original change and tend to destabilize the system. Negative feedbacks dampen initial change and thus tend to stabilize the system. That's a very important point. Very, very important point when we talk about the climate. Linkages between the biochemical cycles and the climate. The most important thing, this is the key to why we worry about the increase of carbon dioxide. It's not ultimately, and we'll see, it's not because of the increase in carbon dioxide as much as the effect on the hydrological cycle. And it says, and this is, I took this right out of the book, is the ocean temperature increases relatively more, the net radiation goes into evaporating water, so that the overall intensity of the hydrological cycle and the atmosphere water vapor content tends to increase. Since water vapor is a greenhouse gas, this leads to further warming, a further increase in evaporation, and so on, as part of a positive feedback loop. It's potentially a positive feedback loop. The increase in carbon dioxide causes an increase in water vapor, here, the increase in water vapor causes warming. Warming causes an increase in water vapor. That's the positive feedback. The increase of warming causes an increase of water vapor through increased evaporation. Increased temperature causes increased warming. That's a positive feedback. That's what people are concerned about, is that. Now, this shows the direct perturbation effect of an increase in atmospheric CO2 and CH4. Look at these figures. This is the effect, pre-industrial 278, this was 360, this is back in 1995, it's changed a little bit, but just to keep that in mind. Not so much on methane, CH4. This is the radiative forcing. This is the amount of additional radiation reaching the Earth's surface as a result of this increase. It's about 1.4 watts per meter squared of carbon dioxide, 0.47 watts per meter squared. So about and probably now just about 2 watts per meter squared and these are the two primary gases, about 2 watts per meter squared. Now remember, we're talking about 342 watts that comes in, 390 that reaches the Earth's surface, so increasing by about 2 watts per meter squared. So it's about a 0.5% increase in the amount of radiation that's reaching the Earth's surface. That's what we're talking about. Now we want to find out though, what impact does that have? This is the physics, okay, we still have 10 minutes, good. The physics of the greenhouse effect. All physical bodies emit electromagnetic radiation. Radiation comes in and it's emitted out. And it's emitted out in the same rate, and we can talk about the amount of electromagnetic radiation that is emitted, and we can talk about that, and it's determined by this equation. This theta times, that's T is temperature to the 4th power, so it's affected by temperature to the 4th power. As the temperature goes up, and that's in degrees Kelvin, it's in degrees Kelvin. As the temperature goes up, there's a big increase in the amount of radiation that a body does. This constant, that 5.664 times 10 to the minus 8 watts per meter squared Kelvin to the minus 4, is called the Stefan-Boltzmann constant. You don't have to worry about that, but just keep that in mind. That allows degrees Kelvin to be converted to units for radiative intensity, so we can find out, as we increase the radiative forcing, what impact that has on surface temperature. So that's what we can use we can use this in order to determine the impact on surface temperature. So this is the emission, the maximum emission possible. This is called a black body. It emits this much radiation. That is the amount of radiation that's emitted. The actual emission is this E, that's less than or equal to 1. So that's the potential. The potential, and this might be the actual. And what's interesting, though, is that for the land and the ocean surface and for thick clouds, it's about equal to 1. The Earth acts as a black body. But for the clear atmosphere, it's between 0.4 and 0.8. And as we'll see, that's why we have the greenhouse effect. For cirrus clouds, it's 0.2, so it's quite, they retain a lot of heat. Now we're going to talk about, this will tell you pretty much everything you need to know about the greenhouse effect. And what's interesting is that it's different. People think that it's about retaining the heat and radiating it back to the surface, and it's not. And this very simply explains it. It's really not that complicated. This is the amount of radiation that's emitted, and it's a function of temperature. So keep in mind, there's the surface of the Earth, that has a temperature Ts, and emission, and it emits as a black body. It emits everything. So the maximum emission is equal to 1, temperature Ts, and here's the atmosphere. It has a temperature Ta that's less. The atmosphere is cooler than the surface. Atmosphere is cooler, and the emission, it emits less. But if it doesn't emit, it absorbs. So it's not emitted, is absorbed. Keep that in mind. If it's not emitted, this emits, it just emits at 1. So it absorbs it and just emits it all. Here, here's the absorption. The EA, theta, so this is the absorption of the emission. This is what's absorbed. This is, but notice that the absorption is at this temperature. The absorption is this. The emission is at a lower temperature. So the emission to the atmosphere of radiation that's absorbed is this temperature. It's emitted at a lower temperature. Okay? So what we see here is that the emission to space by the atmosphere is less than what's absorbed than this term, which is the absorption, because Ta is less than Ts, and that's everything else is the same. And that's simply it. That's the greenhouse effect. I've explained to you the greenhouse effect in 2 minutes. That's simply it. It's that the atmosphere emits less than it absorbs. That's it. So that is that the emission from the atmosphere to space is less than the radiation emitted from the surface and absorbed by the atmosphere. That's the greenhouse effect. And when you put that in the total here, this is the emission. The emission, that's the transmission to space from the atmosphere. And it's done at this temperature. And it transmits at the Earth's temperature. That radiation goes out as if it's radiating from the Earth's surface, because it just transmits through. Plus this, which is the emission from the atmosphere. And that's less than the emission from the Earth's surface. That's the greenhouse effect. That's it. It's not complicated. And that tells you the atmosphere retains more energy. That's simply it. It retains more of the. It absorbs some of that radiation and it re-emits it at a lower temperature. And that's the crucial point, is that the emission is at a lower temperature, so the energy is retained in the atmosphere. The radiative forcing, we talked, because when you increase the amount of carbon dioxide in the atmosphere, is the primary effect. The changes in the surface temperature are said to be driven by changes in the net radiation of what's called the tropospause. Tropospause, we have the troposphere, and the surface. That's the atmosphere immediately above the Earth's surface. The high stratosphere is above the clouds. Most of the interaction is between the surface and the troposphere interact very strongly. The troposphere and the stratosphere interact weakly. The emission that happens, it's at this level, and what happens in the troposphere is what's important. And so because of this, there's an estimation that the change in net radiation due to the doubling of atmospheric concentration is estimated in the Earth's atmosphere to be about 3.5 to 4 watts per meter squared. So if we double the effective amount of carbon dioxide in the atmosphere, it's going to cause 3.5 to 4 watts per meter squared. So now we want to think, well, how much warming does that do? How much warming does that do? And then we get that by considering the radiative damping. So I said that's when there's a change in the radiative forcing as a result of some change in the atmosphere, the temperature of the atmosphere and the surface, they adjust. So what happens is you get an increase in the gas. The increase in the gas causes a forcing. The forcing means there's an increase in radiation at the Earth's surface. That causes an increase in temperature. Ultimately, that's going to cause an increase in the amount of radiation that goes out. You're effectively causing more radiation to come to the Earth's surface. That amount at 390, that amount is going to increase with the increase in carbon dioxide in the atmosphere. So eventually more of it has to be emitted to space, and the process by which you achieve that equilibrium is called the process of radiative dampening. So the important point is the more rapid the increase of long-wave infrared radiation to space with the increase of surface temperature as a result of a radiative forcing, that is an increase in carbon dioxide and methane and other greenhouse gases in the atmosphere, the less the temperature of the atmosphere and the surface need to increase in order to restore the balance and to have what we call an equilibrium. And we know what equilibriums are because we study that in economics. That's that process by which you have supply equals to demand. Here it is the process by which outgoing radiation equals incoming. Outgoing radiation from the atmosphere equals the total amount of radiation that comes in. So the rate at which the net radiation to space increases as a result of a change in temperature from a net forcing change, from a change in the amount of greenhouse gases, is called the radiative dampening, and it's that lambda. It's that term. So we can, the larger radiative dampening, the larger this figure, the smaller the net temperature increase, the smaller the impact. The smaller the dampening, the larger the impact. And we can express it, and this is the we're going to look at the temperature response without feedbacks, and we're going to close. I'll do it very quickly, hang on here. Change in temperature, that's the forcing, the change in atmospheric CO gases, that's the dampening effect. And I'm going to do this very quickly. This last page, please go over this. Don't worry, just worry about this figure. That's the lambda is estimated to be 3.76 watts per square meter. The doubling of atmospheric CO2, as we've said, is between 3.5 and 4 watts per meter squared. So the temperature response without feedbacks is the change in the forcing for a doubling, and that's for a doubling of atmospheric CO2. The doubling of atmospheric CO2, about 3.76 over, well, about 3.76, roughly. So it's roughly about 1 degree Kelvin, which is 1 degree Celsius. That's the impact of a doubling of CO2 in the atmosphere. It's 1 degree Celsius. Now, the reality is, this is what's important, is that ultimately, when we talk about the effect of the increase in temperature as a result of the increase of greenhouse gases, it's not directly the impact. What we're talking about is the effect of the feedbacks. This is not going to cause a problem. 1 degree Celsius change from a doubling is not a big deal. That's not going to cause much of an impact. The impact is whether or not, and the degree, the extent of the feedbacks. And that's what we're going to talk about next time, because that's the big question. That's the big issue. And because of the uncertainty of that, and this is the point I want to make, the uncertainty of the size of the feedback, everybody, we know this, and this is one of the questions you should ask. Just ask anybody, well, what's the direct effect of a doubling of carbon dioxide? And they should know it's about 1 degree. If somebody can't tell you that, then they don't know what they're talking about. Most people do not understand that issue. And if you didn't understand that issue before you came to the class today, I hope that's what you understand now. You understand this, the issue is not the increase of carbon dioxide, it's the feedback effect. And that's what we're going to talk about next time, is what is the feedback effect. And I assure you that one of the things about that is that if we really knew what the feedback effect was, and we thought it was big, the world would be changing real. We'd be doing it now. We wouldn't waste any time. And it's because of that uncertainty as to why it's a much slower process. So, but we'll go through, that's what we'll talk about next time, is to look at the range of what it's thought to be the feedbacks. And in the end, I'm not going to tell you how you're supposed to think about this. I'm going to tell you what I'm predicting is going to happen myself next week. But what I hope that you get out of this is that you'll be able to ask intelligent questions of this, and hopefully much more intelligent than the average person can ask. So, and I'd be curious to know how much of this that you understood. That would be appreciated. Thank you.